I am going to talk about the concept of software, software engineering. This is probably a bit new to you. It was new to me many years ago too. I am a trained scientist, and I'm going to talk a little bit about myself. So that I'm a professor, and by daytime I am the pointy-haired boss and lead a large research group in Stockholm. But I've also been blessed enough that I have software to thank for a very large part of my own career. A large part of my team and I once upon a time developed software that has given us lots of impact in science, but also a whole lot of impact in infrastructure, and there are many other people in the world using our code. And the idea of this talk is to somehow share this with you. Hopefully after this talk, I will have helped you take one step in the direction of, becoming better at coding, but not in the sense of sitting down and hacking code in your editor, but thinking more systematically about how you code. Using state-of-the-art tools, I'm going to show you some, and there will be many slides here with pointers so that you can check it out later. Improving the quality of the code you write, not by being better at coding, but by being more systematic about how you code. And in generally improving the productivity, first for yourself, but second for your team. And I noticed there were a whole lot of questions in the panel here that were on this topic too. There are some good ideas and tips and tricks here that I hope that you will be able to learn. And some of this is really going to be hard effort that we will all have to realize that we should probably spend more time thinking about code and arguably less time sitting down and doing ninja coding. Hopefully, you too will be able to use this to get more impact from your work. People will think that you're a better coder. Other people will be more likely to use your code. And eventually, this should hopefully give you a great career opportunities. And whether that is going to be because you're a university PI and it's just that you're having impact from your code, that's one possibility. You might be working as a research software engineer and have the reputation being the person at your university or compute center that is a master at getting old codes to be better and work. Or you might head out into industry. And if you're in industry, these things are even more important because then you have paying customers that rely on the quality of your code. And if they don't like your code, they're going to go to your competitor. So why am I talking about this? Well, you should do what I say and not what I did. As part of my academic career, we've developed a large code base called GROMACS. It's a molecular dynamics simulation engine, roughly similar to AMBER that Tom Darden has developed. This started out as a fairly small project when I was a PhD student in the mid-90s. And then we figured that there were a few other groups who started to use this. This is fun. And then it started to take off more and more. I think there were probably a few dozen citations my first year for one of these papers. And now I checked lately, I think this year we're going to hit 10,000 citations per year just for the software. So we're getting by the end of this talk, I would have another 2 citations on my software. So there are 30 to 40 papers per day published, 24/7, 365. This code base is completely horrible. And I look at my code, and many of the things I say here about how you should do things, if you look at the code, if we were able to do these transitions, you will be able to make these transitions too. The problem is with this organic growth, initially things are great. And you're creative students and you sit down and code and then you get a friend helping you, and the more work you do, the faster things move. But around 2010, we noticed that some things we were successful, but it was painful. There were so many bugs, and I spent so much time in the debugger in every release hunting down horrible memory errors in C. And we had reasonably good state-of-the-art tools. The source control in those days was called CVS. We eventually switched to Git. And we felt that we had good build tools and everything, and yet something was not working. Because in every year when we made a release, we spent 3 months just testing it. And that the testing phase became longer and longer year after year. And we had a very advanced automatic testing system consisting of the 4 of us. And this is unsustainable, because of course, by the time this would be 4 months, we would be spending a third of our time testing the code, not developing the code. And at some point, you're going to be spending more time testing your code than developing the code. And this is what happened to most code bases. They eventually stagnate, not because they're bad, but they're so full of problems and hacks and everything that you spend more time dealing with your hacks than actually developing the features. So what do you do then? Well, then you yank out your code base and you start off from scratch, and then you do the exact same mistake again, because you start ninja coding and you're making rapid progress early on, and 10 years later you're going to be in the same problem again. So the idea is to break this cycle. Now, you might think that this is only relevant for a code that has 2.5 million lines of code or something, but I'm going to give you a short example here. A small code to calculate pi from 1966 in Fortran. And I challenge in particular the senior professors and engineers here that there are like 10 lines of actual code here. Understanding the control flow in this, I could not do this in 15 minutes. And that's 10 lines of code. And our codes are not a whole lot better. The only difference is that we wrote our codes, and it's easy to understand the control flow in the code you wrote yourself. And if we can't understand this in 10 lines, you're sure as hell not going to be able to understand it in 100 lines. So the point is that you should start this when you have 10 lines of code. Don't wait until you have 1 million lines. So if you learn the good practices here when you have 10 or 20 lines of code, you're gonna spend slightly more time fixing up code initially, but long term you're gonna save gigantic amounts of time because you're not gonna be spending time in the debugger. I hate debuggers. So there is actually a formal definition of software engineering by IEEE, and it's really the application of systematic, disciplined, and quantifiable approaches to both development, operation, and maintenance of software, and I'm gonna come back to that. That is quite different from the way most of us scientists work. I know that some of you in this room are software engineers, and you're much better at this than I am. I'm a scientist by heart. So scientists, we're great. We're trained in physics, chemistry, and we might think that we're ninja coders. We are not. We care entirely about our problem. The next paper is far more important than the quality of the code. Just do a quick hack, fix up the code so that we can publish this, and then we'll clean it up later. No, we won't. Any new code is a new algorithm. That's something we can publish. That's an asset, right? Fantastic. The student has been productive this week. They added 2,000 lines of code. We code on our own, and we usually write more code than we read because whatever, I will fix it later. The proper mentality in software engineering is pretty much the opposite. They don't care about the problem. And remember, we removed the science talks from this workshop, from this summer school. They care about the code, and they care more about the long-term maintenance than the short-term deadlines. The whole point, code is a liability. 2,000 lines of code is a nightmare because somebody will have to maintain these 2,000 lines of code that are full of hacks for the next 15 years. Who is going to do that? Until we know who is going to do that, we don't accept that code. And I recently, just 2 years ago, I refused a gigantic contribution from a major vendor. They wanted to donate an accelerated implementation to GrowMax. I refused to do it because 50,000 lines of code with crappy documentation that we're not going to take on the responsibility for maintaining this long term. You have to hire somebody to do it. And they eventually did, and now they're cleaning this up and adding this piecemeal. And I'm not going to say what vendor it is. But the point here is that in software engineering, reading code is much more important than writing it. And this is where the mistake you make. We think that this is going to slow you down. It will slow you down initially. But the point is that what you forget here is that you will get all the time spent debugging and fixing code back. And that's going to save you time long term. This is related to a wonderful concept called technical debt. So what you do with those quick hacks, you take on a loan, a debt. There is nothing wrong with that, fundamentally. That, well, many of you are young, right? And if you buy your first apartment or a house, it's perfectly fine to take out a mortgage. But just as with a house, if you keep taking on more mortgages, because you're just consuming, right? At some point, you're going to spend all your salary just paying the interest rates. And at some point, the interest rates is larger than your salary, and then you're going to go bankrupt. That's the equivalent of giving up your code after 20 years because you can't maintain it anymore. So those quick hacks are fine, but you have to realize you're taking on technical debt. That debt has to be repaid at some point, or your code will just deteriorate and get worse and worse and worse. And again, you're thinking that you're going to care about this when you have 1 million lines of code? No. You start caring about this when you have 10 lines of code. By the time you have 1 million lines of code, you're making the same mistake we did, and then you're going to spend 10 years cleaning it up. It's only now that we're getting to code that is reasonably good and clean. But you could, of course, argue that this is just important to the research software engineers, the people working at centers. You're a pure scientist, you only care about the science, let somebody else deal with this. And then you might end up in Dave Chandler's and David Limmer's situation. So this is a long story that I won't go into detail about, but for 7 years, there was a big war between two groups about supercooled water and whether supercooled water would condense or not in different phases. Forget about the exact scientific problem. But these groups got different simulations results, and they couldn't agree. What's more interesting, one of the groups refused to share their code. Because they argued, you have the quote there, he argued that he's just a small postdoc, he doesn't have time, you need to clean up and document the code before he shared it. Eventually, 7 years later, through a paper, the other group forced them to share the code, and then they found the bug. So this poor postdoc ruined 7 years of his career. He is a professor now, but you can easily ruin your entire scientific career if you don't share code, if you have code that is crappy, and if you don't use tests. So this is not at all about making the code run slightly faster or something. That if you care about your science, you should care about the quality of your code. You can separate these characteristics of software, and the first obvious way is probably what we think about, being operational, efficient, correct, and everything. Budget is important. You might not think about money, but your time is a budget item. But long term, it's just as important being the translational part. That is the code portable to ARM? Can it interoperate with other codes? And this is not the person doing the coding anymore, right? But can this work as a component as part of a larger infrastructure? And even longer, when the code is maybe not actively developed anymore, is it modular enough that you can replace parts of it? Can somebody else maintain it? Do you have proper documentation that is flexible and scalable, etc.? In proper software engineering, you have to care about all these things. And again, you might think that this is complicated, but when you only have 10 lines of code, this is trivial. It's by the time you have 1 million lines of code, this gets complicated. So I'm going to take you through some of the lessons that we've had for this in GrowMax, and along the way share some of all these tools. There is a beautiful universe out there for open source tools, and since most of you are in academia, pretty much all of these, even the commercial ones, will give you free licenses if you just share your code as open source. I strongly recommend that you share your code as open source. In addition, a few years ago, I created a small repo on GitHub on the previous software challenge. We should update this for the new one. But if you want a small boilerplate thing that you can copy from your own project, this is just like 3-4 source files. Steal this one. You don't need to give us credit or anything. This is going to include pretty much all the cool things I talk about in this talk, and then you have a way to start this at least. When you want to do really advanced stuff, both GrowMax, our code base, and a whole lot of other ones are available on GitLab or GitHub, and then you can check how other people have done it too. So if we start with source control, how many of you are using Git? That is awesome, because I'm not going to have any slides on it. I trust it. You all know that it's a nightmare to keep track of what has changed, right, and everything. But what you might not be aware of is the workflows. Whether you're using GitHub or GitLab, these workflows are slightly different, but I would strongly encourage you to take a couple of minutes to read through how they suggest teams work in Git. So using Git on my laptop is one thing, but I have many different feature branches. Maybe if you're working on this challenge, maybe you have one OpenMP branch, maybe you have one MPI branch of the challenge. Keep all this alive in parallel, and at some point you can have 20 branches that are alive, and then it gets really, really complicated to sync. Now that's fine, because you can switch between the different branches, and it's perfectly fine for you to have 10 branches alive. Until you get to the point that it's not only you developing this. What if you're one person out of a team with 5 people? Because by the time you now want to resync about the cat project branch there, if you want to resync that back, unfortunately the master branch has changed, because I committed my code before you committed your code. So what we use in GrowMax and a whole lot of other large projects is that you constantly rebase. So the blue dots here, that is the main where the master is, and master used to be placed at the old base here, and then I created a separate branch. Now, my branch is not quite ready to be merged yet, but if you learn the rebase commands in Git, if Erwin here has now committed new code, That means that the master has now moved 3 commits forward. Well, I'm not ready to merge my branch yet, but I can rebase my feature branch on the latest head of master. And if I keep doing this every few days, that means that the changes in every rebase are going to be small. So if there are any conflicts in the same file, you can fix those in 5 minutes. And a year later, when I'm actually ready to merge my feature back, it's already synced on top of master. And then it's going to be really easy to resolve any remaining small conflicts. This might sound complicated, but in GitHub or GitLab, this is usually just a button. Click rebase, and it will rebase automatically for you, unless Erwin and I here have happened to edit the same file. Then I will have to do it manually. But 99% of the cases, it's just clicking a button. And in GrowMax, we probably have 100 feature branches in parallel that are constantly being rebased. The other part that I would strongly encourage you to think about is how your commits are. And I'm sorry, I constantly break this rule myself. A good Git commit should be 10 lines. If it's more than 10 lines, you should start having bad conscience. Because 10 lines, 2 years from now on, when there is a bug in this commit, it's just 10 lines. It's going to be trivial to find it. While if this commit from this anonymous vendor we talked about, 50,000 lines of code in one commit, yeah, that's great. If there is a bug there, I will know exactly that it's in one of those 50,000 source lines that was changed. That's when you have to fire up the debugger. If there is a bug that did not happen prior to this commit, but after this commit, there is a bug. There are like 3 active lines I changed here. We already know that the bug is in one of those 3 lines. I don't have to open the debugger. Second, you need to have good comments, what I actually changed. And again, this seems, it's going to steal a little bit of time when you do this, but this is why you don't have to open a debugger. So if you don't like to spend time in debuggers, this is a really good way to avoid it. And I'm going to come back to how we test that these work. You're also building your tools. And as part of the training events here, you've been using make files, where we summarize all the commands so that you can just type make and rebuild the program, right? Ideally, make files are good because it enables you to set different flags for different architectures or so. The problem is that in practice, they are completely horrible. So for 2 or 3 small source files, it's fine. But if I now have 20 different set of compiler flags, and it depends on the version of CUDA I'm using and everything, maintaining these files, they become a nightmare. So friends don't let friends write make files. In some old files, in some old projects, there might be a downloadable make file. And in a trivial project like the one in the summer school, sure, by all means, write a make file. But here, if you're editing make files directly, have a little bit of bad conscience about that too, because you're just causing yourself unnecessary pain. So the way to solve that is, of course, we should automate our usage or creation of make files. And there are tools to do this. For the real world, the real horrible world, you have no idea how horrible computers are, and they're configured in a strange way, and the system administrator configured a library. There are 4 different conflicting versions of the C library. We have no idea whether it's a small or big endian system. The real world is fairly horrible out there. There is an equally horrible tool called CMake that at least solves this problem. So I don't enjoy writing CMake, but it's a lot nicer than writing make files. So with CMake, CMake ships with hundreds, if not thousands, of different tests. And we have, in GrowMax, we use roughly 100 of them or so. And this could, for instance, be if you need CUDA in your project, you can just say, find package CUDA. And CMake will now check where CUDA is located, check what version you're requesting, set up all the compiler flags you need, the flags you need to link with CUDA, and then you just say that, okay, and link with the CUDA library. And that's fine if it's one library, right? But imagine if you have this with 20 different libraries, and it depends on, you might want to leave it up to the user. Should you configure this with CUDA or HIP or SYCL, or do you want to allow both CUDA and HIP at the same time? It's not going to be completely beautiful in CMake, but it's orders of magnitude easier than trying to do this manually. And in this small example, this is the complete CMake list file. And you might think that this is fairly large, but this file, it sets everything up. We have support for MPI, we have support for OpenMP, we have support for OpenACC, we're creating documentation, we have unit tests, we are detecting whether OpenMP is present, we're checking whether these libraries work. We do everything here. And it's still, I should have had slightly more comments here, but we're talking about maybe 50 lines of code. And in general, you don't have to change this very frequently. Maybe if I want to add HIP support here, I would need to update this. Once you've done this once, any user can now just type cmake and configure this on your platform, and it's going to complain, for instance, if you're asking it to use OpenACC, but we could not find OpenACC, it will compile. It will complain rather than trying to compile and then give you an error message. CMake also enables you to do slightly fancier stuff that if you have 4 or 5 different architectures that I'm building in parallel, maybe one OpenMP version and one MPI build, I can actually put the output files, the object files, in different directories. They read the same source, but I've configured it in 2 or 3 or maybe 10 different ways. And if I now change one source file, I can go into each of these directories and type make. And it will likely only have to recompile one file and then relink all the files, which is a pretty big deal in a program with 1,000 files. So I saved 99.9% of the work here. The other part that you should have a bad conscience if you're not doing is documentation. How many of you are systematically documenting your source code? That's hardly none. There are 10 heroes or so in the room here. There is only one place to put documentation, and that's in the source code. If you don't put documentation in the source code, you're going to think that I will update the documentation later. No, you won't. And the tool everyone uses here is Doxygen. It's a semi-old, semi-maintained tool, but it solves the problem. If I use an example from GrowMax, the exact way you use Doxygen, it's not very hard. You have a few commands here that we can say, document whether something throws in C or what parameters are. The reason I'm showing you this example, you start by writing the documentation. In this case, it's a C++ class. So I've started to write pretty much the constructors here, and then I write the documentation. What do I require? What can the user expect from this? And I wrote that before I wrote the implementation. Because now I have the recipe here. This is exactly what I need to implement. If you start by writing the documentation will guide you in the implementation. And second, this is really nice even for me now, 5 years later, remembering what I actually wrote there and remembering what I require. Now, once you've written this, what Doxygen will generate, Doxygen is going to create web pages for everything here, and not just web pages, it's going to have links. So in this interface, for instance, any type that I click here, that's going to be a blue link, and I can click and I will instantly get documentation for that type too. So everything is cross-referenced. And now, that might not matter a whole lot to you because you know your code. Well, I'm getting older, so I certainly don't remember what I wrote this module, but it was 5 years ago, and I don't remember the details. But it's fantastic to remember exactly how I thought about this 5 years ago. This is related to another concept that we could spend a full hour talking about, and I won't have that time, but it's application programming interfaces. This also sounds like something very fancy that you might want to think about when you work at Google. But I would argue this too is something that you should think about when you have 10 lines of code. So the API, that is my promise to the person who's going to use my code. And if I go back to the previous slide here. So this is a module that implements random numbers with an algorithm called 3fry. Exactly what that does is not important. But the only thing that matters if you're going to use this is exactly this, the interface. You do not care about my implementation, as long as I promise you that this interface will never change. And if you call this tomorrow, you're going to get exactly the same random numbers tomorrow. Now, as long as I fulfill that promise, I can change absolutely anything I want inside my black box, make this faster, make it run on the GPU, whatever. But this is a promise that I can't break. And here too, this is why you need to start with the documentation, start thinking carefully about this is the outwards facing part of my module. And again, this is going to take you some time. But the neat thing, we used to have constant problems with our random numbers in GROMACS, and we forgot things that they didn't work in parallel. You got different random numbers running in serial in parallel, etc. For the last 6 years, we haven't had a single issue with our random numbers, because I sat down, I spent 1 week, properly implemented a random number module, and literally, for 6 years, we haven't had a single bug related to random numbers. And prior to that, we probably had one per month. Can you imagine the amount of debugging time that has saved me? Now, that was so worth 1 week of time doing it properly once instead of doing it improperly 25 times. You can find a lot of documentation APIs, and there are entire books written about this, but here too, this is not primarily a programming problem. You can, whether you call this C, C++, Python, or whatever, you need to sit down with paper and pen and thinking about somebody else than you. What should they expect? How do they expect to solve their problem? How will they need to interface with your program? What can you require that they specify, and what can you promise about the returned output? And note, that has absolutely nothing to do with the language in which your module is implemented. So again, dare to spend the time with paper and pen, and then write the documentation, then write the interface, and only in the fourth place you start writing the actual code. But that's great, but if I only start documenting the low-level stuff, that's not going to help me. Because in many cases, you need some high-level document. Why do I need random numbers in the first place? What is the point of my algorithm? That might not belong to a specific source file. We've thought about that. Python comes with a beautiful documentation tool called Sphinx. That's what all the Python documentation is written in. But you can write this in your code too. And not just in code, the equivalent to small README files. This is so-called markup language. It's a very, very simple way of you're using the, for instance, circumflexes or a few dots or underscores to say that it's header 1 or header 2, and then you can even use LaTeX math here. This type of general documentation can be processed with this Python tool Sphinx, and again, you generate beautiful documentation in web pages that are hierarchical in different sections. This can be automatically built too, so that every time I update this in my source code in this file, the documentation is automatically rebuilt, and it's automatically pushed to this site, readthedocs.org. And if you have an open source project, they will host your documentation for free. Did I mention that I even included this in the CMake files for the small project I set up? You know, doing this the first time is a bit hard because you need to learn the document, you need to learn the way to it. But there is probably 5 lines of code in total in the CMake files. So steal somebody else's CMake file. Do this when you have 10 lines. Start by describing why are you creating this repository in the first place? What's the goal of this project? Because to me, 5 years later, if I'm going to update this repository with the new OpenMP version, I'm going to start here. I'm going to start here and understanding why we wrote this and what the point of IHB, CSS is and everything. And it's so much easier to maintain this if the foundations are there and if the foundations are good. And again, it doesn't hurt to get beautiful, nice web pages. So somewhere in all this, we also realized that if we need to be modern, we might actually have to move to modern tools too. So around 2010, GROMACS was a C project. We ditched our Fortran kernels around the year 2000, mostly because our C kernels were just as fast. And that was, to me, it was just a nightmare having to maintain Fortran. Sorry, Erwin. But C, you can say many things about C, but it's not a nice and beautiful language. It's a language that constantly leads to memory errors because you have these dangling pointers everywhere. So we gradually, after a long and hard deliberation, we actually switched our entire project to C++. And we've even switched to modern C++ now. So this week, we're going to change our entire base to require C++ 20. So I don't mind Fortran. It's a nice language. But modern C++ has some really beautiful parts. Everything like threads, atomics, and everything, it's part of the native language. You don't have to rely on external packages. In C++ 23, you even have parallel algorithms as part of the standard library. Modern containers, hashes, and everything, it's built in the language, just like in Python, but where these implementations are horribly slow in Python, in C, they're extremely fast. And it's also a language that you can use to enforce strong modularization and data encapsulations to really make sure that, again, if Jay and I both write codes, I can make sure that I don't peek into Jay's code by mistake and vice versa. The negative part here is that while I know the C standard by heart, I know the part that is undefined behavior in the C standard. I could probably implement a C compiler. With C++, after 10 years, I still consider myself a beginner. So it's an extremely large and complicated language. And that also means the mistake everyone does when you start out with C++ is you think you're going to use all the features, and that leads to horrible spaghetti code that is completely impossible to maintain. So the biggest challenge with C++ is really that you need to be very restrictive and decide just to use a subset of the features. I'm not going to go through this in detail, but Herb Sutter of Microsoft and Bjarne Straustrup have developed the C++ core guidelines. And there are essentially a way to make sure that tie one hand behind your back, so write code that is reasonably good. This is good enough that large parts of the flight control system in the Joint Strike Fighter are written in C++, following the C++ core guidelines. So you can use C++ for very sensitive and security important software. What I like with C++ is that it's a powerful language that you can hide things that are really complicated. So if you used OpenMP in one of these trainings, we occasionally use low-level threads so that I program threads natively. And then you need mutases to make sure that, that some areas that only one thread at a time can be part of it. That's easy. You lock a mutex, you do something, and then you need to unlock a mutex. What all of us then forget, we forget to unlock the mutases, or I return early, or something happens. And then you get these data races or something, and that's a complete nightmare to debug. Well, in C++, you have classes. So I can create a mutex class that when I initialize it, I automatically lock the mutex. And in C++, the second I reach the end of this block, I will automatically deconstruct the class. So it will automatically unlock this mutex. You can do things even fancier with shared pointers or so to get rid of things if you copy them or so. But let's now assume that somebody here starts to copy this class, and then I will need to change my interface, and I'm not going to go through in details why, but I changed this to a shared pointer. So I've changed my entire implementation here on the left. But on the right, so this is the beautiful part of C++, that it helps you do this type of data encapsulation and modularization that as a user, you won't know now that the implementation here is better and can also handle things. We potentially fix the bug here, but the person only using this class won't see anything. Yes? Sorry? It probably is. It's 5 years ago.